A lot of people have trouble with trigonometry. They have trouble understanding it, what it means, why we have it, and why it's actually kind of important. So I made this video to teach you trigonometry in a different way. It's a way I've never seen taught, and it's a way that helps me understand it better because in actuality, I'm kind of stupid. But I know why you're really here. You just want a new memory aid, don't you? You just want an easy way to memorize things so you can get through trig and just get it over with and go on with your life and yada yada yada. Isn't that it? Fine. SOHCAHTOA isn't working for you? I'll show you something different. First, look at your calculator. At the buttons for sine, cosine, and tangent. You don't have one handy? Well, let me show you a shot of mine. Second, all you gotta do is sing. And here's a little ditty by Frankie Lyman and the Teenagers. Take it away, Frankie. Need that again? Okay. Still need more? All right. One more time, Frankie. And there you have it. A new memory aid, a new way to memorize something in math so that you can think less about it, theoretically. Now you can go back to binge watching your sitcoms.
Bye. Have a beautiful time.
You still here? Did you sit through all those commercials just to see what was in the rest of the video? Wait, you skipped the ads, didn't you? Even worse, you have an ad blocker. How could you? I mean, all those people worked so hard to make a commercial to try and get you to buy crap you probably don't need. Someone went through the trouble of going through your browser history so that they could target you with ads for stuff similar to the crap you've already bought, and you just stopped them from having any effect. So mean. Oh well. But I guess if you're still here, then it means you were smart enough to realize that the video went on after the ads and that you really want to understand trigonometry and why it's kind of important. Okay, here's a definition of trigonometry. Yeah, it's cropped out of some web search. The branch of mathematics dealing with relations of the sides and angles of triangles and with the relevant functions of any angles. This is not how to think of trigonometry. You want to learn how to think of trigonometry? This is what you do. Turn your head to the left. Now turn your head to the right. Now turn your head to the left again. Why are you shaking your head no at me? I got you. Yeah, yeah. I'm cool. Yeah. Anyway, look up. Look down. And now look back at the screen because you actually do think I'm cool. And now that you've done all your neck stretching, let's analyze the world. What you just did was perceive the world at one angle, then another angle, and so on. You observe them all from some point of origin. You. The universe exists in 3 dimensions, and the most efficient way to analyze these dimensions is for our axes of measurement to be orthogonal, or perpendicular to each other from some origin point from each other. And for that, we need a way to translate our 360 by 360 view of the universe to an orthogonal grid, and vice versa. And that's where trigonometry comes in. So the reality is that we're not looking at triangles, but rather we create triangles to interpret and analyze our 3 dimensional world. The triangles aren't the study, they're the consequence. Everything that exists in the universe is based on circular and spherical motion, even a straight line. And if you don't think that's true and don't think that's possible, well, then I got 2 words for you: Fourier analysis. Go ahead, look it up. I'll wait, and you can come back when your mind's exploderated and you want to learn how you can understand that concept better, because it all starts here. Trigonometry is the final step to understanding how things are positioned in the universe. So, let's begin. But first, some review. Here we have a circle. Let's do a little quiz of what the different parts of a circle are and how we define them. Now, if you don't know any of these things, don't feel bad. Feel really bad. Precious knowledge has been withheld from you. or you're just a slacker who never bothered to pay attention in the first place. If you forgot them, however, it's okay. Mathematics is mostly about understanding, but some of these names are going to become important. So, here we go. What is this, and how would you define it? As many of you probably have said, it's a radius. We can define a radius as a line segment from the center of a circle to any point on its circumference. The radius is actually the most important thing of a circle because it defines everything about that circle after its definition. This is why you'll start hearing the word radian more often from now on in math. A radian is just the length of a circle's radius. Think of it like a piece of ribbon that, even though you bend it around and crumple it all up or whatnot, it still maintains the same length. Okay, enough of that definition. Next one. Again, what is it, and how would you define it? Another one probably many of you got. This is the diameter. It's a line segment that terminates on 2 points on the circumference and intersects the center. Notice how I'm using very specific wording with my definitions. This is important in math in general. But back to our review. Next one. What's this? Does it strike a chord? Math humor. Yep, it's a chord. It's defined as a line segment that terminates on 2 points on the circumference. Notice there's only a slight difference between the diameter and the chord. One is on a circle, and one is made by Honda. Okay, seriously. In order for a chord to be diameter, it has to also pass through a center. So the diameter is a chord, but a chord may not be a diameter. Next, this should be fairly easy. It's an arc. It's a portion of the circumference of the circle. Next, now some of you might have a little trouble with this one. This is a tangent, which I'll try not to go off on. A tangent line, or line segment, is identified because it only touches a circle at one point and remains entirely outside the circle. The line is then said to be tangent to that circle. Now, it may seem from the image that the line is touching the circle in more than one point and actually touching over the area. It only looks this way because of the thickness of the lines that I've used so that you can actually see what's going on. In reality, a one-dimensional line has no width and cannot be seen, like magnetic flux. Now, for one many people don't know, this one. This is called a secant. A secant is a line or line segment that goes across the circumference of the circle through 1 or 2 points. You can think of it as what a chord becomes if you make it grow longer while in its same relative position. Okay, review time is over for now. Some of these things will show relevance pretty soon, but to get into actual trigonometry, let's go back to square one. A circle and its radius. Remember, we have a 360 by 360 view of the world, but to start, we're going to work in only 2 dimensions. To work in 3 dimensions, you just have to repeat the process, but work off of different axes. Speaking of axes, let's add a couple. There we go. Now we're on the Cartesian plane. First thing that you have to remember is that we can rotate the circle while it's on the plane. Just like we can reflect, translate, and dilate. All stuff you should have known from geometry. But these concepts will make working in trigonometry easier as well. To note rotation on the Cartesian plane is the opposite direction from a windrose. Going counterclockwise is positive degrees. Going clockwise is negative degrees. It's also different in origin from the windrose as well. 0 is at the top of the windrose, while on a Cartesian plane, 0 is to the right, because the x-axis denotes our real number line, and it becomes more positive as you go to the right, and more negative as you go to the left. So with this circle centered at origin and a radius drawn, we're going to indicate the angle from the x-axis. And because we like the Greek alphabet so much, we algebraically label this angle theta. Now, the point we're interested in is the point where the radius meets the circumference. In my ever so extensive, like really extensive amount of research. Like, oh my god, I spent so much time doing it. I don't think I ever had time to even do this video. All right, never mind. I searched for something, but I couldn't come up with anything. I couldn't find an officialized name for this point, so I'm just going to call it Bob. Bob is very important because we are looking through the lens of a radius. Bob provides us information about what is called a vector. So Bob can be the object that you're looking at, or whatever. A vector has two pieces of information: magnitude, which in this case is the length of the radius, and a direction, which in this case is the angle theta. Vectors apply to everything. Like I said, where an object is in relation to you. It also is the force your ass is exerting on your chair, or the velocity that I'm traveling in a relatively downward direction after the alcoholic effects have sapped me of my consciousness. There are actually many different ways to write vectors because trigonometry and various forms of notation allow these different ways to be interchangeable. For example, if I said the coordinates 2, 7, you would know that I'm referring to 2 over and then 7 up on the Cartesian plane, magnitudes and directions. So realistically, vectors are nothing new to you. What trigonometry allows us to do is interchange Bob from a vector using length and degrees of rotation, which is known as a polar form, to one of the various rectangular forms. Now, when you learn trigonometry in school, there's going to be a lot of words thrown at you, and you're going to be told that they're functions, and here's what you do with them, and it's pure crap, okay? And feel free to tell your teacher that is pure crap. Some person making a video on the internet, gives you this authority, and you know you should always believe everything on the interwebs. Instead, we're going to look and define lines and how they relate to Bob on the circle. So the first line we're concerned with is the radius. We all know what this is by now, right? Good. Now, let's make lines that identify the x and y values of Bob. Now, let's define them. And I know you probably don't want to hear more definitions right now, but trust me, once you see them, it's going to make things extremely helpful. This vertical line is the sine. It's the vertical height of Bob. And you can see the length of your definition I wrote on the screen. Anyways, this gives us our y value of Bob. This horizontal line is the cosine. It's the horizontal displacement of Bob. So remember in English, the prefix co means with. So this is a line with the sine, cosine. And the cosine gives us our x value of Bob. Now, we have this rectangle, and what do we know of rectangles? Oh yeah, opposite sides have the same length. Oh, would you look at that? A triangle. Hopefully, a light just clicked on in your head. In which case, I would call you Uncle Fester or tell you to stop electrocuting yourself, whichever would be more applicable. So at this point, we have Bob on a circle and the sine and cosine, which gives us the relative distances on the x and y axes relative to the radius. Hopefully, things are starting to make a lot of sense to you. But for now, let's just store this information. And there we go. One important thing to take note of is that there is a vertical component, in this case the sine, a horizontal component, in this case the cosine, and a diagonal component, which in this case is the radius. If you're clever, you're probably noticing that some theorem applies right about now. And if not, don't worry, we'll get into it later. Now, what happens if the radius is the horizontal or vertical component, or if there are lines that extend outside the circle you probably didn't ask? Very good question. Let's look. We'll start with the radius as the horizontal component. There we go. Radius is our x value. Now we need a vertical component and a diagonal component. There's two important things we need to observe. The first is that the vertical and horizontal components shouldn't meet at the origin. If they did, there'd be no fucking point to all of this. The second is that the horizontal and or vertical should only touch the circumference at one point, Bob. So let's add a vertical line that starts at Bob. Any idea what we call this line? Maybe something from what we already know about circles? That's right, a tangent. It's going to give us some height. Now we need a diagonal, something to give us our straight line vector or polar form, since we already have our rectangular values. Any idea what to call this line? It's not as easy as the last one, but you do know the word already. It's called the secant. Look, it's a line segment traveling across the circumference of a circle. In trigonometry, it's important that it connect the opposing ends of the radius and the tangent. Otherwise, it doesn't really serve a purpose. But would you look at that? It's another triangle. Once again, the lengths of the secant and tangent are dependent on the length of the radius and the angle of rotation. You know what? Let's store this ratio along with the others. Now, if you've already started learning trigonometry, and once again, you're clever, you probably noticed there are a couple different trig identities and where they come from. And once again, if not, don't worry, we're going to go over it later. Let's first go to the situation where the radius is the vertical component. This time, I don't know, it might seem kind of counterintuitive. It's going to feel like things are upside down. Just remember, everything here goes along with everything on the last circle we looked at. Nevertheless, let's start with our radius. And Bob. Along with last time, we need two components. But this time, we need a horizontal and a diagonal. I wonder how those two lines would compare with the last set. That's interesting. Oh, but there's a problem. I see the angle is still on the axis and not side the triangle. There's only something I knew about triangles and other related geometric shapes that would allow me to extrapolate some information. That's better. Now, what's with the names of these other lines? Whatever could we name them with? All right, that's enough of that. There you go. Cotangent and cosecant. They have the same idea as a tangent and a secant, and along with the tangent and the secant, the cotangent and the cosecant perform a similar function. Except that, unlike the tangent, the cotangent is horizontal. But you can see that realistically, it's still the same triangle, just rotated and dilated. All three triangles that we have made so far are similar to each other. It's just that the important piece, the radius of the circle, has equated to different parts of the triangles that we have made. So once again, let's store this information. All right, take a second to acknowledge it. Compare the sides. You see it? Yep, it's just rotation, no funny business. Some people get thrown off unless they flip their monitors upside down and right side up and back and forth because they're just not good with spatial awareness, which is fine. Okay, we're all good now. Oh, by the way, if you haven't been writing all this down this whole time, then shame on you. I thought you wanted to learn. The exercise of association through exertion by taking notes and immediate practice is actually one of the most effective ways to learn things. But we're not here to talk about the mechanics of the human neuron. We're here to talk about ratios. If Sally has 3 apples for every 5 bananas Frank has, how many apples does Sally have if Frank has 20 bananas? I'm serious. Answer the question. You should have said 12 apples. It's actually really important that you be able to answer this question properly because ratios are the heart of trigonometry. The entire foundation of trigonometry is being able to identify a line's relation to the radius of a circle and finding the ratio between the lengths of those two segments. That's it. Still confused? What was that ratio in that previous question? That's right, 3 to 5. There's actually many different ways to write a ratio. We can write it with a colon, for example. We can also write a ratio as a fraction, showing proportionality. Well, it is a fraction, and it doesn't stop being the same ratio if whatever I do to that fraction doesn't change its value, so let's complete the division. 0.6. It's actually another way to write a ratio. Before calculators had trigonometric functions, we would have to solve trig by looking at all these ratios in decimal forms on all these sheets, and it was annoying. It would take up time. But now we have calculators, and no one knows what the fuck is going on because no one explains anything anymore where this all comes from and where the foundations. Hence this video. So ratios are the heart of trigonometry. Now, back to our triangle that we stored. All the trigonometric functions are just shorthands for ratios, writing the individual ratios based on wherever our angle of rotation is. For example, the sine function of theta, which is how you read this, is really just the ratio of the sine to its radius. Likewise, the cosine function follows. Different function names represent the same sides on similar triangles, and all of them have their own respective radius. Oh, that's a lot of radii. Let's make some annotations to keep everything in order. Got it all now? Good. It's all just nested similar triangles shown on one triangle. Now, let's look at one of the first trig identities you will learn or will learn. Remember, these values just represent same sides on similar triangles. So let's set up a proportion, shall we? The tangent divided by its radius is proportional to the sine divided by the cosine. You see them on their respective sides? Well, as we just learned, we can write the tangent function in shorthand. As for the other side, let's divide the top and bottom by their respective radius, and then convert to the shorthand. Then, this should seem familiar to some of you. Let's look at something else. This is a right triangle. Along with the right triangle, we have a certain theorem, because the radius is a hypotenuse. Now, looking at this, let's divide everything by the radius squared. And now, we're going to convert to trig functions to simplify. And also simplify the right-hand side, because anything divided by itself is 1. Seeing more things come to light now? It's important to remember that a triangle can be rotated, reflected, and so on. Remember, a triangle just represents information about a circle. So first, you need to establish where your origin is going to be. It should be on the horizontal, away from the right angle, where the angle theta is. It doesn't matter which way the information you are presented is oriented, because you control how you approach the information. So if you need to, just twist your damn paper around. Let's get to the important question. If all I know is the angle, how do I know what the ratio is? I wouldn't worry about calculating it out by hand for now, since it would take a really, 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 really long time to do so. This equation goes on infinitely, which at first seems daunting. After all, it's a very tedious process. The easy part is that it follows a pattern. X minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus yada 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 ad infinitum. And in case you don't know what a factorial means, here you go. It's just taking each integer until you get to 1 and multiplying it. So 5 factorial is 5 times 4 times 3 times 2 times 1, and so forth. And the equation for the cosine ratio is similar. And for those of you who are already in calculus, you can see their relationship through a differential lens. Ha 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 ha. Okay, that was really bad. These equations are actually stuff you'll learn in Calc 4, but I wanted to show them to you now to give you an idea how concepts can seem complicated yet simplistic at the same time. No one's going to expect you to do this out by hand while you learn trigonometry. Instead, they'll give you overly complicated equations with trigonometric functions in them and lie to you and say it's part of the study of trigonometry when really they're just algebra and really convoluted algebra you'll probably never see, just so that you can apply the trigonometric identities and formulae so that you learn in different fashions. As far as calculating the actual ratio based on the angle, this is one of the only times that I've ever told students to go ahead and use their calculators. Just make sure you learn how your calculator works, because some calculators require you put in the function first and some require the angle first. Now that you know what the functions are and what the lines represent and how to calculate the values, let's talk about something that might not be intuitive for you, but it's also equally important: the inverse functions. After all, what's the point of having a notation for doing something without the ability to say that I want to undo it? I'm going to put this to the side for a moment and talk about something else that you should be familiar with: exponents. I'm not going to go that deep into exponents. I just want to reference one thing. Let's say I have this statement b equals a. What if I want to divide both sides by b? How would I write that by using only exponents? There. B times the inverse of b, which is 1, equals a times the inverse of b. I want you to remember that, because when it comes to the inverse of trigonometric functions, we use it completely wrong. In trigonometry, we use the inverse function rather than the inverse of the value. Sorry, we use it to indicate the inverse function rather than the inverse of the value. There, I even said the line wrong. That should indicate to you how wrong we use it. Although other notations using exponent refer to it as the multiple of a value. You see? You see? This is the shit I gotta deal with. What asshole decided this was a good fucking idea? Fuck that guy in the dick with a rusty pitchfork turned sideways. Ah, that's better. At any rate, it's referred to as the arc sine. And similarly, you have arc cosine, arc tangent, and so forth. Either notation is used to represent the same thing. Most importantly, we have a way to indicate, or we have to indicate, what does each mass statement translate to. In the first case, the question is, what is the ratio of the sine to its radius for the rotation of angle theta? In the second case, the question is, what is the angle theta that will give me the ratio of this sine to its radius? Again, the statements are, I have the angle, what's the ratio? And I have the ratio, what's the angle? Now, the final part to prepare you in understanding applications of trigonometry. Back to our original viewpoint, where the radius touches a circle is at some vertical height and some horizontal distance. Let's once again spin this circle. As the circle rotates, the sine and cosine lengths change, and also change between positive and negative values over time. The circle can rotate faster, slower, and in both directions. This will be something fun to look at in more detail later. There you go. It's done. Happy? That's great. If you like this video, I don't give a shit. If you want to see more videos like this, then wish in one hand and shit in the other and see which one fills up first. Bye.